there is a unique variance measure, and then the ratio for those intervals here are covariant. So in general, people have a number of critical points. The degree of criticality is a discrete invariant, but then you have also the ratio of probability among by the invariant measure is a continuous invariant. So the question is whether those are the only invariants. That is, if the moduli space has finite dimension. That's it.
And here it is. Does every mass of diffeomorphism have some physical measure? Okay, so we know what an mass of diffeomorphism is. The question is, if you are in a mass of diffeomorphism, do you have at least one measure whose basin of attraction in the orgadic sense has positive Lebesgue measure? Does everybody understand why this is an interesting question and not something that... Yes, yes. So... Yes, that's a question. So this is a bit of a trick question because we were supposed to be a bit shocked by ignorance here, because everybody knows that anosal diffeomorphisms, transitive anosal diffeomorphisms have a single physical measure, and I know that, I'm not that ignorant. The question, as Christian has noticed, is it true for C1 anosal diffeomorphisms? As far as I know, there's no counterexample. There's no example of a C1 diffeomorphism, anosal diffeomorphism, which of course will not be any more regular than C1, which does not have any physical measure. So I'm pretty sure this is open. I think it's probably a very difficult question to answer. So the second version of the question, which is weaker and maybe easier to solve, is this. Does every, it's in fact the same question, but generic anosal diffeo have at least one physical measure, and if we assume that they're transitive, as they might all be, we would very much like this physical measure, if it exists, to have as a basin of attractor the whole manifold. So a full Lebesgue subset of the manifold. And so the first one is, does every anosal diffeomorphism, and here the interesting is C1, and here I'm saying, okay, I'm asking a weaker question. Generically, C1 generically, is this true? One would hope that it might be, and the naive way to approach this would be to say, okay, if you're a C1 anosal diffeomorphism, you can perturb, do a small perturbation, and then you become C2. And if you're a C2, then you do have a physical measure, which has a full basin, and then by some sort of semi-continuity, some sort of lower semi-continuity, maybe this property goes down to C1 generic anosal diffeomorphism. But the problem is that we don't have anything that's semi-continuous to hold on to here. Okay, if you think a bit about it. So this naive idea will not work by itself. Some new ingredients, and I don't know what they are. I thought about it with some other people. We don't know how to solve it. And the third question, and this is where I'm driving at, is does every, and by the way, maybe this has been asked by somebody else, but I don't think it's been written down. Maybe somebody here can correct me. Does every C1 generic diffeo, transitive if you want, or not transitive if you don't want, have at least one physical measure? For example, if we take a non-hyperbolic robustly transitive diffeomorphism, is it true that modulo C1 perturbation, so densely, maybe generically, does it have a physical measure with the full basin? I don't know whether this is true. I'm pretty sure that this question here, as I stated here, is open, but I'm not sure. Lately there have been lots of very pathological constructions of robust or generic diffeomorphisms with very weird behaviors, and maybe if we take a good look at one of them, we will find that they're counterexamples, that they don't have a physical measure, or that they have some physical measure, but that it's has a very small basin. I don't know. So that's the question.
Natural number, and here you have, let's say, so this is a complex number. Take here the norm, the model of the complex number to the square minus 1 divided by v minus aj, is the model of the number to the square. So here the condition is like this. These numbers, they are positive numbers, let's say natural numbers, and this AG, they are complex numbers. Which model is bigger than 1. So this is a positive number, and here is a negative number. And the V here is on the tip. I mean, so model of V is 1. So the problem is the following. If let's say let me make a draw here. You have here a complex plane, and you have these numbers AJ. Then what I want to say is the following. If two of these numbers are in the same ray, departing from the origin, so I will state like this. If, let's say, AJ is equal to theta times AI, so this theta will be bigger than 1. Then FZ at most so I think for 0. So it must be for 0 only 2. Maybe I can arrange it here. This concludes saying that there is at most 4 zeros on S1.